your TA here. So we had some confusion in office hours about 3.20 in the homework, and it's kind of a beast, so I just kind of wanted to cover over it. So this is a reference node problem. I'm sorry, this is a supernode problem. So a supernode is when a voltage source is connected between two non-reference nodes with any element connected in parallel with it. So I'm gonna put that down here real quick. And this is in your textbook. I believe it's page 110. Okay, so also kind of note, this is a reference node. We call it ground. So basically the idea is that zero ground is the reference. So kind of imagine this was some velocity problem in Newtonian physics. You have your ground, literally the ground, where your ball is rolling, and that is our reference point. So that's why we call this a reference node. Then the ball can either go left or right, or it can go up, whatever. It's Newtonian physics, we don't need to deal with it. But in essence, zero is our reference point. Everything's with relation to the ground in the circuit. So that's where reference is. Thus, non-reference node is like V2 and V3 and V1 up here, okay? So also meaning these two corners are not nodes. They're tied to ground, so they are technically part of the reference node. Okay, so coming back to the supernode concept, it looks like there are two, but in fact, because this is connected to what we see as one node, this is connected to it as well, so this is all one supernode, okay? And that looks ugly, but it is. And I can try and redraw the circuit a little bit to kind of drive it home, but the way we solve these, we don't need to actually redraw the circuit this time. So we have to treat supernodes differently than every other circuit, because there's absolutely no way to know. Wow, that is hard to see, huh? Let's use this color. There is no way to know what I supernode is, because it's across a voltage source. And our understanding of circuits right now, there is no resistive element here. We have a voltage, but we need a resistive element by Ohm's law to be able to find a current here. And here as well. We cannot find the currents across these two stems. So since we cannot know them because of our understanding with Ohm's law at this point, So we have to do some funny things, and they're not too funny. They're just fiddly bits. They're just, you gotta recognize the situation, and then you gotta apply the right rules. And that's basically the core of electrical and solving these kinds of, or really any circuit analysis. Cannot find no current across voltage source. Okay, so what we have to do is treat this circuit a little differently than normal. So this is where things get a little bit funny. So we have to use both KVL and KVC. So these are Kirchhoff's voltage and current laws. These are the things that say some of I really did write this. Oh, heck. There we go. Sum of currents into a node equals 0. And KVL is sum of voltages around a loop equals 0. Okay, so we have to use both of these to be able to kind of figure out what the heck is going on here. So what we're going to do is we're going to kind of redraw the circuit when we apply both of them, because different things happen when we apply them to the supernode. So first thing we're going to do is the voltage loop law. So KVL. So what we're going to do is we're kind of going to ghost out the rest of the circuit. We are just going to look at the supernode. So that is the voltage source on top, down to V1, across to the current controlled voltage source. And we know it is a voltage source because it's indicated with a plus minus. We know it is current controlled because its characteristic value is given to us as a function of some current somewhere else in the circuit. Okay? And V2. And we're just kind of gonna... Oh yeah, and this one down to V3. And then we're just kind of gonna not look at the rest of it. Yeah, sure, there's stuff going on here, but it doesn't really lend itself into the voltages of the supernode. So all we care about is still this. So we're going to write a voltage loop equation on it. So 0 equals, and I'm gonna go this way. I default to going clockwise. It makes my brain feel better. So we're gonna start here with the 240 volt. So since I am coming out this way, we are exiting the minus, but the current that we are following to make this loop will enter this device in the positive side. So this is a positive 240 volts. All right, then we're going to enter this V3 on its positive side, okay? So this is going to be plus V3. Now, we're going to enter this V2 at its positive side, plus V2. Then we are going to enter this current controlled voltage source at its negative side, so this is going to be minus 20I. And then we are going to enter, and this one's a little bit of a stretch, okay? So, minus, we are coming in to the negative side of this V1. So there's our KVL equation. Now what we're going to do is we're going to apply Kirchhoff's current law. And so now we're going to draw the circuit just a little bit differently. We are now going to ignore the supernode. So now we've got nothing special happening up here, nothing here. V1, nothing special here. V2. That's not a voltage, that's a resistance. These actually do matter. And this is also a resistor. And we're gonna go get the values of these. 20, 10, 40, and 40. Okay. So, just to put scary words in the air, you can kind of think about this as a superposition. And I know that that word has a lot of baggage around it. It sounds like it's a mess, but the truth is that when we are mathematically doing a superposition, we are basically saying, okay, but what if it's in both situations at once? And we're kind of looking at that use case from both sides. So in this case, our KVL is from the voltage side, and it looks at the supernode itself. And KCL is from the current side, and it looks at what happens around the supernode, so that we get this whole picture of the circuit. So what we're gonna do here is we're gonna write the currents that go into or out of this equation, or this node. And we're gonna pretend this is just one big node. Everything then enters or exits this node. So we are gonna write V1 minus 0, because we're starting here. V1 is part of our supernode, and its current will traverse this from the ground, the reference node. So V1 minus 0 over 40. Then we're going to add this V2, same deal, minus 0 over 10. And then we're going to take this I, which I is actually going to be V3 minus 0 over 40. Okay, so you might have noticed that I ignored this voltage, or this, I mean, there is a voltage there, but I ignored this resistor. And the truth is that that resistor doesn't affect anything. It is kind of just absorbed into the supernode for all intents and purposes. We don't look at it because it's kind of contained in the supernode. You kind of notice how it doesn't add a voltage in, and it doesn't add a current in, because basically these are, you can consider this just two connections of the same node, so really there's not a current going through that. And I know that's a little bit of a stretch, but just go with me on it. So this will all sum to 0. Now, you might notice a problem here, and that problem is we got a lot of variables. We got I, right? We got I, and I is up in this one too, right? And we've got V1 and V2 and V3. Holy smokes. We are swimming in unknowns, and my god, we've only got 2 equations. So what are we gonna do? We are going to find relationships. So we are going to first, because it's the easiest one, we're gonna look at this I. So I is the current that comes out of this node down this branch. And this branch goes straight to the reference node, straight to ground. So this is like the ideal case of just apply Ohm's law. So I equals V3 over 40. Bam. Cool. So now we've got 3 unknowns and 2 equations, or you can say it's 4 unknowns and 3 equations. You know, it's we got it in terms of something else that we need to find anyway. So we're just gonna hold this aside. It's probably gonna be a Masca tool for later. Next thing we're gonna do is we're gonna try and relate V1, V2, and V3. And we can't do that all at once. But what we can do is start by pretending there's 2 supernodes here, okay? So there's 2 voltage sources. One is current controlled, yes, but it's still a voltage source. So we're going to break these off and write 1 loop for each voltage source. So we're gonna start here and snake around this way and snake around here and pretend that there's nothing else underneath it. So that loop is going to be, so again, following the same convention, it's going to come into this 240, so it's going to be positive 240, into the positive side of V3, so plus V3, and then minus, because it's going into the negative side of V1. And I know this doesn't look like it's going into the negative side, but let's just go with the thought that if it's going into the top of a voltage, or the plus sign if it has one, then it's positive. If it is going into the bottom side, or the negative sign if it has one, then it is negative. That's just a convention, it's just a decision. If you decided that all voltage sources were upside down, you just better make sure that you keep it consistent. Everything about this engineering practice is keep your conventions consistent. If you have to write them down at the top of your page, do it. I have done it for years. So it's fine. Use whatever you need to, do whatever you need to make this easy on you. Okay, so anyway, this is our first one. So this is how we're gonna relate 1 and 3. And that's... You might be asking, okay, boss, but how are we gonna connect 1 and 3 and 2? So the next thing is we're going to do the same thing around this voltage source. And we're gonna start here, and we're gonna loop around and into there. And so basically what you'll notice is that if you pretend, not that there are two supernodes, but if you pretend there is one supernode per voltage source, then you get these relationships. And basically both equations that will come out of those will have a V1 term. They share V1, which means that we can solve for the non-V1 variable in both equations and have them both in the same terms. And that is how we're going to equate them. Alternatively, you could solve them both for V1, set those two equal to each other, and then solve, and then you'll have the relationship between V3 and V2. It's just however you want to do it, but this is the most straightforward, I think. Okay, so anyway, we're going to start here. We're going to come into the positive terminal. Please stop. Positive terminal of this 20i. So we're going to have positive 20i. We're going to come into the positive terminal of V2, so plus V2. And then we're going to come into the negative terminal of V1. V1 equals 0. So what we're going to have is V2 equals V1 minus 20i. And we're going to have V3 equals V1 minus 240. So these are our other equations. These are the missing link. So I'm just going to rewrite them down here. Oh, what color did I make that? V3. Okay. V3 equals V1 minus 240 and V2 equals V1 minus 20i. And we have I, and we have V3. So let's go ahead and plunk that in. So I becomes V1 minus 240 over 40. And so V2 becomes V1, and that's a V1, minus 20 times V1 minus 240 over 40. And that's 2, and that's 1. Yeah. So, cleaned up, we get V2 equals V1 minus V1 over 240 over 2. And yeah, I know that could simplify more, but I'm not going to do it. I'm a grown-up, I make the rules now. V3 is V1 minus 240. And I equals V1 minus 240 over 40. So now with these, we can start solving through. So what we're gonna do now is work with our current and voltage equations. So we're going to plug these in and get everything in terms of V1. And then we can solve for V1. And then we can back solve for V2 and V3 and I, which we will need, but you know, I is going to be in terms of V1, so it won't matter. So we can solve for everything now. because we have enough equations. And we have the correct relationships. So yeah, I guess I can just work through that now. It just might be a little boring to watch, but let's see here. Okay. No. Minus 20i, which is, well, we'll do that all once I've written it down. V1. Okay. So V1 plus 20 times V1 minus 240 over 40, which again is going to be 2 and 1. We do minus V1 minus B1 minus 240 over 2 minus, hold on, let's set ourselves up for success here. 240, there we go. So let's see here. And honestly, we only need to solve one or the other of these since they're all in terms of V1. We should be able to solve it through get V1 and then just plug it into everything else. If you want to do this anyway, that's perfectly fine. You could set it up in system of equations in a matrix, or do it this way, but with take a hammer and fix the equation, or, you know, whatever. I'm not here to judge your math. I'm here to look that you understand the engineering concepts. So, like, if you want to chug this into something, just do it. Just tell me, this was how I set up the equation, put it into Wolfram Alpha, this is what I got out. That's literally all I need. I, however, am going to do this small brain style and do it by hand. Anyway, V1 minus 240 over 2 is plus minus V1 plus V1 plus 240 over 2 minus V1 plus 240. Okay, we have 1 minus 1 minus 2. I'm sorry, that's just -1. Sorry, that is... I am already setting a very good example. Okay, now we have V1. Gonna cross those out because I handled them already. Okay. We have some more color. V1 over 1/2 plus V1 over 1/2 is plus another V1. I'm going to end up proving that 240 equals 240. Yep. Nope. Not doing that. Okay, so we are actually going to use not the voltage circle, but the current. After all, we already used the voltage, so we used the voltage law to get these associations. So we can't use KVL again. All right, so once you've got these, and you're going to turn this in, you're going to put this into the Kirchhoff current law that we got, which was V1 over 40 plus V1 minus 20I over 10 plus V1 over, V1 minus 240 over 40 equals 0. So you're gonna put these in here, solve for it, and get the solutions. I'm going to write them here. V1 is 60 volts. V3 is minus 300 volts. And V2 is 90 volts. So this is what you're gunning for. Let me know if you've got any more questions. And also, terribly sorry about my confusion. It's just been a very long time since I've touched Supernodes. But I will try and stay on top of things from now on. All right. Later.